Welcome. This is the lecture 2 of heat and material balance, and in this lecture basically we will discuss the RIST diagram based on overall heat and material balance in the blast furnace. First of all, we will develop the RIST diagram based on only oxygen balance, that is the material balance, and later on we will also add on the overall heat balance of the blast furnace. So, concept covered basically here oxygen balance and the RIST diagram, and the RIST diagram with overall heat and material balance. These two things will be there. First of all, we will discuss the oxygen balance and the RIST diagram. So, now before doing that material balance, let us see the different elemental balance that is there in the blast furnace. Basically, we can consider the iron balance. Just we consider there is the iron coming from the ore that is going into the hot metal, we have discussed in elaborately. Then carbon balance, that is you have coke, there is the carbon is coming from the coke mostly, and the two sinks are, one is the gas, another is the hot metal. And now it is basically the same balance in terms of this the carbon balance. If we see per gram atom of iron basis, then we can write like this, where NCI is basically total moles of carbon input per gram atom of iron produced. Similarly, NCA basically represent, that is the gram atom of carbon that joins the blast furnace gas, and that is called the A stands for active carbon. Okay. So, that is the gram atom of carbon that join the blast furnace gas per gram atom of iron produced. And C by FEM is basically, that is the carbon, gram atom of carbon that joins the hot metal per gram atom of iron produced, that is the C by FEM. Similarly, the oxygen balance, if you see in the blast furnace, what are the source of oxygen? One is the ore, another is the air blast. So, you can find ore is the one source, another is the air blast. That is the two major source of oxygen in the blast furnace. And you can always say that is the from the gangue also some of the oxygen is coming, but we are considering that is the gangue that is coming, a part of the gangue also going through the slag. So, whatever the oxygen coming, that is going out, and part of the gangue get reduced. So, they also contribute to some extent to the oxygen into the blast furnace. Okay. But we are ignoring that thing. That is because of silicon reduction, phosphorus reduction, some oxygen obviously join the blast furnace gas. So, that much of oxygen for the time being we are ignoring basically to make it simple, because we are just developing a predictive model now. Okay. So, it is a very simple predictive model, and if I just oxygen balance, if I consider in terms of gram atom of iron basis, then it will be like this, O by Fex, that represent, that is the gram atom of oxygen that is input into the blast furnace to produce 1 gram atom of iron, right. And then NOB represent, there is the gram atom of oxygen input through the air blast to produce 1 gram atom of iron. So, that is equal to basically there is O by C in the gas, that is the gas composition, basically oxygen to carbon atom ratio, that basically gives you the gas composition. Okay, O by C multiplied by NCA. NCA is the gram atom of carbon that joins the gas per gram atom of iron produced. So, if you multiply that, that gives you basically gram atom of oxygen, that is the right hand side full term represent gram atom of oxygen that exit the blast furnace gas to produce 1 gram atom of iron. So, this is the thing, and then I think it is obviously now it is, this is the final equation, that is the oxygen balance equation, and if I just write, that is the O by Fe, basically this represent. So, O by Fe basically this represent the gram atom of oxygen input, gram atom of oxygen input through, right, through iron ore to produce 1 gram atom of iron. So, this basically this term gives you, there is a gram atom of oxygen input through iron ore to produce 1 gram atom of iron. Similarly, this similarly gives, that is the gram atom of oxygen input through air blast, right. I should have write it air blast. So, this is basically, this is also the gram atom of oxygen input through the air blast, this is the gram atom of oxygen input through the iron ore, all to produce 1 gram atom of iron. Now, I will just click it. Now, this thing and right hand side, this term basically represent gram atom of oxygen living through BF gas, blast furnace gas, for gram atom of iron produced, right. So, this is basically, if you multiply this thing, this is the gram atom of oxygen living through the blast furnace gas per gram atom of iron produced. This is the gram atom of oxygen that is coming in per gram atom of oxygen coming in through the air blast. This is the gram atom of oxygen that is coming into the iron ore, and this is the gram atom of oxygen that is leaving the blast furnace gas, all for per gram atom of iron produced, right. So, now this diagram, if you see, so this is basically, this line basically, if you consider this one, this thing, you can consider it is the equation of a straight line, y is equal to mx plus c. Basically, it is y is equal to mx plus c. If you just take the NOV on the side, minus of NOV. Okay. So, it is basically an equation of straight line where this basically represent this point basically represent a minus of NOV in OB. Okay. So, this is minus 1.4, basically NOV is equal to minus of 1.4, you can find it is negative already. So, gram atom of oxygen that is entering through the blast. Okay. So, this thing, this part gives you the intercept, basically gives you the gram atom of oxygen that is in through the blast. Okay. And this is the O by Fe positive axis, and this is the O by C blast gas composition. So, it is the straight line, equation of straight line. The slope basically, so intercept basically give you the NOV, that is the minus 1.4 is equal to NOV is equal to 1.4, or it is that is this thing, and the slope that basically gives you, the NCA. NCA is the active carbon, that is the active carbon is given by the slope, and this basically gives you the gas composition, that is the O by C is equal to 1.4. So, from this simply the operating line. So, here what you can find, if you define two parameters, the third parameters can be defined. So, what I want to mean, that is the, by knowing the two parameters, like you have the three parameters, one is basically NCA, one is NCA, another is the NOV, another is the O by C. There is O by Fe, we know, it is known, O by Fe for hematite is equal to 1.5. For hematite ore or Fe2O3. For Fe2O3, O by Fe, basically per gram atom of iron, basically it is 3:2, that is 1:5, 1.5. So, 1.5 is the input ore, and so we have basically three unknown here. This is this and this. So, gas composition, active carbon, and the air blast, oxygen in the air blast, these are the three unknown. If I know two of them, we can calculate the third one. So, it is we have 2 degrees of freedom basically here. So, if we know the two item, we can calculate the third one. So, then there is the coke rate can be calculated by knowing the blast rate as well as the exit gas composition, O by C and the NOV. If I know, I can calculate the coke rate, NCA. So, NCA is the active carbon, and then we can convert it to kg per ton of iron produced. That can be done. And deep intercept, basically large air blast requirement. The deeper the intercept, it shows there is a large air blast is required, and optimum slope will depend on the enthalpy balance and equilibrium requirement, that will come later on. Okay. So, it is a very simple operating line based on oxygen balance, and that gives you the coke rate. You can calculate the coke rate. If you know in there is a blast furnace is operating in a steady state with a certain blast rate and the gas composition you can calculate what was the coke rate. Or if you know the coke rate in a blast furnace and you know the gas composition, you can predict how much air blast you have to provide. And if you know how much air blast it is taking and what is the carbon rate, so then you can calculate the composition of the gas. So this is what, by the simple oxygen balance, you can calculate an operating line. This is the simplest operating line of the blast furnace. Now let us do a simple problem, that is the composition of the top gas from a hematite charged blast furnace is composition is given. Your 22 volume percent CO, 20% your CO2 and 58% is nitrogen, and the blast volume also given. Okay. Now from this data you have to calculate the coke rate, right. So what we'll do, this is the equation that you have to consider, and then O by Fe is 1, hematite charged blast furnace, hematite Fe2O3. So oxygen to iron ratio is 3:2 is equal to 1:5. That is, if you want to produce 1 gram atom of iron, that is the more oxygen that is coming per gram atom of iron is basically 1.5. And then O by C, how do you calculate? O by C is the gas composition. Now O is the gram atom of oxygen that is present into the exit gas, and carbon is the C is the gram atom of carbon into the exit gas. So oxygen you can calculate. How do you calculate? What is the gram atom of oxygen? If I know the moles of CO and CO2, I can calculate how much gram atom of oxygen is there, because in CO 1 gram mole of CO contains 1 gram atom of oxygen, but 1 gram mole of CO2 contains 2 gram atom of oxygen. So if I know the moles, so what I can do, NCO plus 2 into NCO2, that will give you, that is numerator will give you the gram atom of, that is the numerator, this thing will give you the gram atom of oxygen. And the denominator, basically you can see both CO and CO2 contain 1 gram atom of carbon only. So therefore NCO plus NCO2 if you do, that will give you C. So now moles is directly proportional to the volume of the gas, right. So you can, I know the volume percentage of CO and CO2, because I know the volume percent of CO is 22 and volume percent of NCO2 the CO2 is 20. So 22 plus 2 into 20 divided by 20 into 22, that gives you 1.476. As I know in the problem it is given that 22 volume percent is CO and 20 volume percent of CO2. So you can simply calculate the O by C by this formula. And then NOB you can calculate, because I know the blast volume is 1400 normal meter cube, and out of in the blast volume oxygen is there, we just multiplied by 0.21, because 21 by volume percent is oxygen in the air blast. So 1400 into 0.21 gives you the volume of oxygen divided by 22.4, right. This will give you the kg mole of oxygen. This will give you the kg mole of oxygen, right, and multiplied by 2, that will give you the kg atom of oxygen present. Now NOB is basically per gram atom of iron produced. Now if you are producing 1 ton of iron, and 950 we have done because 1 ton of iron contains 5% of carbon, okay, that is given in the problem, the 5% carbon. So 50 kg carbon is there into the hot metal. So in hot metal contains effectively 950 kg of iron, right. And 950 kg divided by 56, 950 by 56 gives you the moles of, what is that, iron that is present into the per ton of hot metal. Per ton of hot metal or product iron, you have 950 by 56 kg mole of iron. So you have to multiply by that thing, that is you have to divide it by this thing, because this is 1400 normal meter cube of blast volume. This normal meter cube is equal to per ton of iron. So per ton of iron you have 950 by 56. So you have to multiply by this thing to get the NOB. NOB is basically gram atom of oxygen that is coming through the blast per gram atom of iron. So you have to divide it by the total number of moles of kg moles of iron that is present into the hot metal. So NOB will gives you simply 1.547, right. And similarly, if you can calculate the NCA now you can calculate directly from the formula. If you just apply the formula, you will get it is at 2.06, and active carbon rate, that is the active carbon rate, because active carbon rate you can now calculate 2.06. Basically NCA is the gram atom of carbon that is joining the gas, right. per gram atom of iron produced. So, this is the active carbon rate 419, and then total carbon rate is basically you have to add the 50 kg, because 50 kg carbon already joined the hot metal. So, 409 is the kg of carbon that is leaving the gas per ton of iron produced, and 50 kg carbon join the hot metal per ton of iron produced. So, total carbon rate is equal to 469, right. So, the coke rate is basically, because the coke contains 90% carbon in the problem given, so it will be 521. So, this is the simple way you can calculate. So, only thing is that you have to convert, that is for gram atom per gram atom of iron produced to this is a kg per ton of hot metal. That simple conversion is required, and you can use the simple equation like this. This is stoichiometric equation. So, this is there. Now, we will come to the enthalpy balance. Now, this is very important, because based on oxygen balance we have calculated, right. That is we have got the operating line, and in that case we find that is the, if I know the two parameters, the third parameter can be calculated. There are basically three unknowns, out of two we can. Now, if we can do an enthalpy balance of the blast furnace, then we will see we can decrease the degree of freedom, our freedom, that is the number of, that is the one variable. If I just give you one variable, then you can predict the other two variables. So, let us do the enthalpy balance also, because without heat balance the blast furnace will not operate. Okay. So, if I do the heat balance, now what are the assumptions? First let us make, now we will make an overall heat balance of the blast furnace, and we will consider a very simplistic assumption we will make. We are considering the iron ore, carbon and air all are entering at 298 Kelvin, that means at 25 degrees centigrade, all are entering at room temperature, and the blast furnace gas also living at the room temperature. So, this is a very simple blast furnace diagram, and then input output statement. So, you can find here in this case, that is your air, you can find air is entering at 298 Kelvin, air is entering 298 Kelvin, and here the ore Fe2O3 plus carbon, okay, that is the coal or coke, there is the coke and the Fe2O3, all coke and ore are coming at also 298 degree Kelvin, and your hot metal is only living at 1800 Kelvin, and your top gas like CO, CO2, nitrogen is also living at 298. So, everything is 298, input is 298, input means ore and coke are entering, and flux also entering at 298, and air blast entering at 298, gas leaving at 298, only the iron, this is the hot metal, is coming out at 1800 Kelvin. That is the thing we are considering. So, let us make an energy balance, enthalpy balance. Okay. So, enthalpy, now as I said, if I do the heat balance, that is the enthalpy into the furnace per mole of iron produced. This is what is the total amount of enthalpy that is in per mole of iron produced. Okay. Similarly, that should be equated to enthalpy out per mole of iron produced, right. So, what are the input? If I say, then input I can find is that through the Fe2O3, that is the ore. Okay, I am considering the gangue is not considered here, because that will take care in the slag formation. So, Fe2O3 basically, where input enthalpy through the Fe2O3 is simply can be represented of H0 298 Fe2O3. And how much moles is there? There is the moles of Fe2O3 that is required to produce 1 gram atom of iron. So, it will be obviously NFe2O3 will be half, because 1 gram atom or 1 mole of Fe2O3 produce 2 gram atom of iron. So, half mole of Fe2O3 will produce 1 gram atom of iron. So, NFe2O3 will be half, and the standard enthalpy input through the Fe2O3. Now, we can say in the left hand side we have not considered any other enthalpy, because the carbon is also at entering at 298, and it is mostly living as gas at 298. So, carbon input 298, output also at 298. So, we are not considering air, oxygen and nitrogen entering at through the air, that is coming at 298 and living at 298. So, we have not considered the any other input, only input enthalpy input we have considered the Fe2O3, because when the Fe2 you require some amount of heat has to be given for decomposition of Fe2O3. Okay. So, we consider only the standard enthalpy of Fe2O3, because Fe2O3 enter at 298 and then it will decompose, as well as the iron will have some sensible enthalpy, because iron will live at 1800 Kelvin. Right. So, this is the input enthalpy is this. Only we considered Fe2O3, we have not considered carbon or the air blast because all are living at 298. Only a part of the carbon can go to the hot metal, but we have ignored that thing. Okay. And the right hand side, what are the enthalpy? You can find there is the iron, there is the liquid iron is there. So, standard enthalpy of liquid iron at 1800, that will be there. And also you will have other two enthalpy, that is the gas that is living. Okay. So, number of moles of CO living into standard enthalpy of CO, okay, plus CO2 into CO, that is the moles of CO2 into standard enthalpy of CO2, because heat of formations are involved here for both for CO and CO2. Now basically what you can do, because the standard enthalpy of any oxide MXOI you can write like this: heat of formation of MXOI plus standard enthalpy of M as well as standard enthalpy of oxygen. But at 298 all elemental enthalpies are 0. So, this is basically 0 and this is also 0. So, basically a standard enthalpy of any oxide at 298 basically heat of formation of that oxide at 298. So, for that thing we can write this equation as, simply we can write this equation at, there is the NFe2O3 plus heat of formation of Fe2O3 on the left hand side is equal to standard enthalpy of liquid iron plus number of moles of CO that is leaving the gas and heat of formation of CO, and the number of moles of CO2 that is leaving the gas into heat of there is heat of formation of CO2. So, this is all the values are at 298, right. And if you rearrange this term little bit, that is the, if I just rearrange those terms, then I can write this equation as a heat demand and supply, where demand part on the left hand side you can find that these are the term is there. What are the demand? This left hand side is the demand, that is the standard enthalpy of liquid iron plus basically this thing, that is the NFe2O3 minus of heat of formation of Fe2O3, because heat of formation basically when iron and oxygen combine to form the Fe2O3, and that is an exothermic reaction. But here just reverse is taking place, we are decomposing the Fe2O3, it is highly endothermic. So, since basically HF, heat of formation of Fe2O3 is negative, so this negative term, negative and negative, it will be a positive term. Okay. So, basically we have in the heat demand is this term, and on the right hand side you can take this thing on the, if you just arrange this term you can write in this way. So, you have a demand term like this, on this demand term you have this and this, that is the sensible enthalpy of liquid iron, and there is the total standard enthalpy of liquid iron plus heat of decomposition of Fe2O3 total. So, basically this liquid iron enthalpy is total, if you calculate it will come around 73,000 kilojoule per kg mole of iron produced. Now, it is coming basically all the thing that is basically iron at 298, you take it to iron at 1873 and also add the latent heat and all these things, because you have to make it liquid. And so, this is the total enthalpy of the liquid iron, and this is the decomposition of Fe2O3. So, this total around 486,000 kilojoule per kg mole, right. And if you consider the slag formation also is there, and if you add up another 100,000 kilojoule per kg mole of heat demand by the slag formation, it will come around 5, there is the 586,000 kilojoule per kg mole. Okay. So, this is the demand. And now, what are the supply term? Right hand side is the supply. This is basically the supply term. Supply basically heat of formation of CO and CO2, because when the CO is forming, carbon and oxygen reacting CO and CO2, that is basically the supply. Those are the supply term. So, those are basically the supply term. So, right hand side this term is basically the supply, right. Now, I am just making some new that is the algebraic manipulation, that is the NCO gas, that is the NCO moles of CO you can represent in terms of mole fraction of CO multiplied by the total moles of carbon present, and then NC and mole fraction of CO you can write 2 minus O by C, because you can get it from here directly. As we said, there is the O by C we have written as, that is your NCO plus twice of NCO2 by NCO plus NCO2. This is what we have written. If you just then you can write simply NCO by NCO plus NCO2 plus twice of NCO2 by NCO plus NCO2. Now, this is basically first term is XCO plus 2 of XCO2, and then it is XCO and the plus 2 of 1 minus XCO. Okay, so it simply comes 2 minus XCO. 2 minus XCO. So, O by C come around 2 minus XCO, that is the XCO mole fraction of CO you can write in terms of O by C and 2 minus O by C of gas. You can simply do that, it is not a matter of things. And similarly, you can represent NCO2 as O by C minus of 1, right. This is the way you can write. And now you can just, so if you substitute all this thing, and the heat of formation of CO is basically minus 111,000 kilojoule per kg mole, and similarly heat of formation of CO2 is minus 394,000 kilojoule per kg mole, and then by after algebraic manipulation, source you can write in this form. This will be the source term. If you just algebraic manipulation you can do that, the source term. And then on the operating line, we have done the enthalpy balance, and we have developed a relation of demand is equal to supply already, and also we have done the material balance, and we have the material balance statement is like this, and our enthalpy balance also we have done, and whose statement is like this, that is demand, actually that means this is the supply, that is equal to demand. Okay. Now, from these two equation, basically it will be 1 minute just. So, this is basically demand is equal to supply is equal to this thing, right. Demand is equal to supply is equal to this thing, and the material balance is that. If we combine these two equation, how do you combine? Basically, I will eliminate the O by C from both this equation. If I do that, then we get the combined equation like this. We got the combined equation like this, that is O by Fe plus NOV minus D by 283,000 is equal to NCA 172,000 by 283,000. And if you can just rearrange this, some algebraic manipulation will give you this type of formula, and this type of form. Okay. And this you can basically write it as basically simply y2 minus y1 is equal to m of this is x2 minus of x1, where y2 is this term whole term is the y2, and this minus of NOV is basically y1. This is your y2 and this is your y1, right. So, y2 minus y1 is equal to m into x2 minus x1. So, it gives basically equation of a straight line. And if you see, this is the equation that you are getting. So, where this is the coordinate of x1 y1, this is the coordinate of x1 and y1, and this is the coordinate of x2 y2. These are the two coordinates you can find, x1 y1 and x2 y2. So, you have a straight line, right. Straight line equation is there. So, you got this line. So, what you can find now in this operating line, I have a fixed point here. I have a fixed point is here. This point is fixed, because for a particular heat demand in the furnace, you have to pass through this point. You have to pass through this point. That's why for a fixed demand, operating line must pass through a fixed point H called the thermal pinch point with coordinate x2 y2, and that is like this. So, x2 is equal to, that is 172,000 divided by 283,000, and if you see, this number is basically 0.61, and the y axis and the y2 is O by Fex, that is 1.5 minus heat demand by 283,000. For a particular heat demand, its value is as I am showing is 0.57. So, if we know this point, basically you can calculate. So, since this is a fixed point, you can easily calculate this point. If you know the heat demand and O by F, you obviously know what is the charge. If it is hematite 1.5, if you know the heat demand, you can calculate what is the H point, a fixed point on the line you know. So, you now require only one point. So, either this point or this point. If you know this point or this point, if you know this point, because this point is known to you, If you know this point, you can have the straight line. So you can easily predict this also the slope. So if you know the blast rate now, then you can calculate both the coke rate as well as the gas composition. Unlike in the previous case when we did only the oxygen balance, then I need to know the two parameter to calculate the third parameter. Here basically I need only one parameter and other two parameter I can calculate. So I have 1 degrees of freedom is reduced now, right. So for example, if I know the coke rate, then I can calculate what is the blast rate as well as what is the gas composition. If I know the blast rate, now I can calculate what is the coke rate or what is the exit gas composition. So this way now only we have one parameter has to be defined to define the other two parameters. So 1 degrees of freedom is reduced now. So it is not still fully predictive. For fully predictive, when 2 points I will get on the straight line, then it will be a fixed line, and then that will give you the minimum coke rate. Okay. Now you can see under this condition you can have the operating line. So the permissible operating range, it shows the permissible operating range, but all the line you can find it is passing through, all the line is passing through this point. This is called the thermal pinch point. So all the line passing through this thing. So it can operating range, the product gas can be either CO, completely CO when the O by C ratio is 1, or the product gas can be completely CO2 when the O by C is equal to 2. So as a result you can find when the product is complete, the exit gas is complete CO2, then obviously your blast rate is less because your CO utilization is very high, CO utilization, and when the product gas is only CO, your blast rate will be more, but both the line is passing through the thermal pinch point such the overall heat demand of the furnace is met, right. So the operating line must pass through the thermal pinch point dictated by the heat demand in the blast furnace, right. So this is what I want to say. If you just do the thermal balance, so I have got one fixed point on the line, but it is not the optimum range, that is the permissible range. Now the line can be like this, line can move over this range starting from exit gas CO to CO2. Okay. So anywhere it can lie. Now if you want to get a optimum line, minimum coke rate line, then you need another point on the line such that the line become fixed and the coke rate become minimum. So to do that, we have to deduce one more degrees of reduction. There is degrees of freedom we have to remove that thing. So when the degrees of freedom will be 0, that is I will have a fixed line, right. So for that I have to do a heat balance later on, that is I have to bring in one more point. How we will do, we will just discuss later on. So estimation of the optimum line in the permissible wave is the aim of the fully predictive model. Okay, that we have to do that. Now let us solve one problem, simple problem based on this thermal pinch point. So the heat demand of a hematite charge furnace I have given, there is a 600,000 kilojoule per kg mole of product iron produced. The carbon rate is 500 kg per ton of iron. The product iron contains 5% carbon, and you need to calculate the volume of the air blast and which is required to keep the furnace operating in steady state, and the composition of the top gas. Two things you have to calculate. Your coke rate is given. So both the parameter now you can calculate. So in previously, that is when the oxygen balance was there, two parameter was have to be given, then the third parameter you can calculate. Now you are given only the coke rate and you can calculate now what is the exit gas composition, what is the blast rate, that you have to do. So I am just simply, the solution is there already. First you calculate the thermal pinch point. So you know the demand 600,000, you just put it there. So you get the point 0.6 and minus 0.62, this is the thermal pinch point. And coke rate also you know, because a carbon rate is 500 kg, out of which 50 kg goes to the hot metal, because hot metal contain 5% carbon, that is equivalent to 50 kg per ton of iron. So if you just minus it, then 450 divided by 12, that is the kg mole of carbon per gram atom. NCA means per gram atom of iron produced, and you are producing how much of gram atom of iron? Per ton of iron, gram atom of iron is 950 by 56. Okay. So that's why you have to, because it is 500 kg, that is the coke rate, that is the carbon rate we are giving per ton. So, you have to convert it to per gram atom of iron produced. That is why I am dividing it by 950 by 56. So, if you do that, NCA comes around 2.21, and NCA is equal to, and then once you get the slope, that is the NCA is basically the slope, and simply, and you know the thermal pinch point. Okay. So, you know the thermal pinch point here. So, in this case you have now this point, this is one point is there, this point is how much, that is 0.6 and minus of 0.62, and you have the coke, there is a slope, you know, slope is what, slope is 2.21, right. So, if it is known to you, then this NOV, this point, that is, this is basically your, what is x, x is 0 minus of NOV, right. So, you know the slope, you know the 2 point. So, from there if you just write this in this form, and you can calculate the blast rate. So, blast rate means gram atom of oxygen that is required from the air blast to produce 1 gram atom of iron is 1.95 that you have calculated. So, from there you can calculate the blast volume. 1.95 is the gram atom of oxygen that is required by the air blast, divided by 2, that is the gram mole or the kg mole. Basically, you can write, if I consider this kg, there is the, you can consider the kg mole of oxygen, right. And this kg mole of oxygen, okay, and kg mole of oxygen multiplied by 950 by 56, because it is per gram atom. So, multiply by the amount of the kg atom of iron that is produced, multiplied by 22.4, that will give you the normal meter cube, and 100 by 21, because this is the oxygen volume, basically this is the oxygen volume. So, this is the air volume, 100 by 21 you get the air volume, that will be 1760. Okay. So, next that is the, you got the gas volume, and then what is that, a gas composition, you have to calculate the gas composition. So, again similarly you can do that from the coke rate, you know, and from this point, that is from this end you can have this now. So, this is the point that you have to calculate, that is your, what is that, that is 1 point, that is the O by C in the exit gas, comma 1.5. Okay. This is the point, and you know the coke rate, slope, you know, slope is equal to 2.21, and you know the, that point also, you know this point also, H you know as how much, H is equal to your 0.6 and minus of 0.62. So, this point and the slope you know. So, you can calculate O by C in the gas, O by C in the gas you know, and so O by C in the gas, that is why the, what is the mole of CO you can calculate, basically total moles, there is moles of carbon, there is the kg mole of carbon into mole fraction of CO. So, if you know the mole fraction of CO multiplied by the moles of carbon, so it is the moles of CO that is present. And XCO again can be written in terms of O by C like this, as we have done in the last class, you can see. So, this is the related, and then you can calculate, this will be the number of moles of CO, similar number of moles of CO2 will be this, and if I know the NOV, so I can simply calculate what is the moles of nitrogen, this thing. So, total moles is given by this, and then gas composition is simply 0.688 by 5.39, there is 13% you will have CO, 19% CO2, 68% nitrogen. So, it is simple, this is the way simple material balance you can. So, this is the thing that you can calculate, and you can consult the book of Iron Blast Furnace Theory and Practice by Davenport, and it is there. So, for detailed study, that is so the RIST diagram based on overall heat and material balance has been demonstrated, and we have seen that for based on the all the oxygen balance, we have 2 degrees of freedom. If we just introduce the heat balance also, we have reduced 1 degrees of freedom. Okay. And so, this brings in a fixed point on the operating line called the thermal pinch point. So we are looking for another fixed point on the line such that the line become fixed and we can predict what is the optimum coke rate in the blast furnace. That we will do in the next lecture. Thank you.